Now, while Faraday's law is usually first discussed in the context of a loop of wire, it turns out there's a much more general way to look at Faraday's law, and we'll start by considering what happens with a charge in a loop of wire. Now, if I have a loop of wire and I have a changing magnetic flux, Faraday's law for a loop of wire says there's going to be an electromotive force pushing that charge around that loop of wire. And the size of that electromotive force would be equal to the change in magnetic flux with respect to time with a minus sign, because nature's trying to make the charge move to cancel the change in magnetic flux. Well, since that electromotive force is pushing that charge around that loop of wire, subject to some resistance, that electromotive force is doing work on the charge. And the work being done by that electromotive force would be equal to the charge that I push around the loop times the EMF that I get from traveling once around the loop. Well, from the definition of force and work, the work being done by a force is equal to the dot product of the force and the path. Well, that force would be uniform all around that path, and in order for a charge to move, a charge moves with an electric field. So the force acting on that charge would have to be equal to the electric field inside that loop of wire times the charge. And the total distance that that charge moves around that loop is just the circumference of the loop, 2 pi times the radius of the loop. Well, equating those two definitions of work, the charge would cancel out, and that tells me that the electric field inside that loop of wire should have a strength that's equal to the EMF divided by 2 pi times the radius. Well, we talked about Ampere's law in an earlier chapter. Ampere's law talked about an idea of a magnetic circulation. And we said if we had a constantly turning magnetic field acting around some path, the total magnetic circulation had to be produced by some sort of current traveling through the area of that Amperian loop. Well, here I would have a constantly circling electric field that keeps changing direction. So I could take this piece and express it as the integral of the electric field acting along some element of path. And for the circle, that would just be the electric field times 2 pi times the radius. That would have to be equal to the EMF. And this brings us to the much more general form of Faraday's law, which states that if you have any changing magnetic flux with respect to time produces a circulating electric field. And the circulation of the electric field around any closed loop is equal to minus the change in magnetic flux of the loop created by that path for working with that electrical circulation. Thanks for watching.